even start this reaction, before you even start this problem, if you were given one like this on the test, you don't automatically assume this is balanced. This is, but don't automatically assume it's balanced. Even if it has some coefficients in there, don't automatically assume it's balanced. This one is, though, 4 phosphoruses, 2 and 2, 4 phosphoruses, 5 and 2, 10 oxygens, 2 and 5, 10 oxygens. The bottom one is also balanced here, but don't always assume that. He could work in a little bit of review from balancing chemical equations into the same problem. Okay, so this is now balanced, and we know it's balanced. So we want to find our intermediates. So our intermediates are coming from a top equation to the equation under. It's something that appears on the right as a product, and then appears on the left again in the equation under that. So what is that?
Can you repeat that?
So we're looking for our intermediates. We want to find our intermediates.
It's the P2O5.
So this is an intermediate. So what we are going to use the intermediates as is to get from equation to equation. Otherwise, there's no way to get from here to here without going through P2O5. Okay. So what we're told in this problem is we started off with 5 grams of our phosphorus, and it's reacted with 6 grams of the O2, and we're wanting to know which reactant is excess. So this is a limiting reactant problem, and we're wanting to see, since they're both reactants, both of the quantities were given, we're wanting to see which one's going to run out first. So you have to work them at the same time. Okay, and our product that we're going to be ending up with for this one is going to be our P2O5. Oh, I'm sorry, it's going to be our phosphoric acid. Okay, so we're going to have to go through both of the equations here. So first, we want the molar mass of the P4. So somebody did the calculation for the molar mass of P4.
129.9.
129.
Wait. I think 123.9.
123.9. Can you go a little further on your decimals?
Well, I started doing it a while back.
Okay. All right.
I can do it again.
No, you're fine. I'll do it. So let's see here. Someone may beat me. I hear someone's calculator going. I'm gonna use my app. So let's see here. So 123.895050 grams per mole. We'll do the same thing for the O2 here. So we're working on both at the same time. 99880 grams per mole. Okay. So then we want to start working through our balanced chemical equations now. So for the for the P4, you're starting off here. No coefficient, so it's understood that the coefficient is 1. So for every 1 mole of P4, what's your coefficient on your intermediate here, your P2O5? 2. So you're going to have 2 moles of your P2O5. Okay. What that automatically does is that automatically drops us down to this next point, and we have to immediately put in the coefficient for that. So what is that? 1. So 1 mole of P2O5. And then we want to jump from here, since this second equation has the point we want to stop. We're not jumping to another intermediate, we're jumping to where we want to stop. So what's the coefficient for where we want to stop? 2. So 2 moles of your H3PO4 or your phosphoric acid. Okay. Now then you have one more step because we want to get back to grams. So for every 1 mole of P3H3PO4, how many grams, what is the molar mass of the H3PO4? Okay, so I'm coming up with 97.995183. Maybe coming up with something a little bit different than that depending on which periodic table you're using. Okay, so I'm actually going to move this down a little bit because I'll run into that answer if I don't. So we're going to do the same thing with the O2 now. Okay, so what's the coefficient for the O2 here? 5. So for every 5 moles of O2, what's the coefficient for our intermediate still? For your P2O5? 2. So every 5 moles of O2, you get 2 moles of your P2O5. So that's going to ferry us down to that next level, which the coefficient there is 1. Okay, and from there we can jump with coefficient of 1 to the coefficient of what? So 1 here, what's our coefficient here? 2. 2. So 2 moles of your phosphoric acid. Still have the same last step here though, so you want to get from moles to grams, so we're going to use the molar mass for your phosphoric acid. 97.995183. So then you would calculate these two out, and what you're going to get is that your limiting reactant is going to be whichever one is less, whichever one gets used up first. Okay. So doing this one here, so 5 grams, multiply everything on the top together, and then divide by everything on the bottom. So you take 5 and multiply it by 2, and then by 2 again, and then by 97.995183, and then divide that by this molar mass. And then the rest of these are all 1, so they're not going to make any difference. So your final mass production from the original P4 you started with is going to be 15.81, so 366, so 15.8 grams will be your production of phosphoric acid. So that's the first part. Now then the second part is going to be your production from your O2. So you're going to take 6 grams times 2.
I multiplied it out for you. It's 14.6998.
So 14.7.
Yes.
Okay. So which one is less?
The top.
The bottom one.
Wait,
Which one's less?
the bottom.
Which one's less production?
Oh.
The bottom?
The bottom. So this one is only going to produce 14.7 grams, and that one's going to be producing 15.8. So your limiting reactant in this problem is your O2. So that's your limiting reactant. Okay, so it asks us for the reactant that's excess. So if this is your limiting, which one produced more?
The top one.
The top one. So your excess reactant is the P4. And then he says what mass of it remains. So if this is how much would be used up in producing that, you would take your 15.8 and subtract your 14.7. Somebody tell me what they get. My number's gonna be a little bit different than
I
his.
got 1.1.
1.1.
Yeah. That's a lot off.
Let's see if I put a number in wrong somewhere here. Hang on a second. Oh wait, I'm sorry. Okay. I see what I did. So if this is going to be the maximum production that you can have, what you need to do now is then take this and work back through this top part, and that'll tell you the grams remaining. So now we're going to do this one in reverse, but instead of starting with 5 grams of your P4, you're starting with 14.7 grams of your phosphoric acid. And all of these conversion factors are just going to be in reverse, okay? So what's going to be here? To get out of grams and into moles. Your molar mass. .183. And then your conversion factors are just going to flip. So you want to get out of your phosphoric acid into your intermediate. So 2 moles, instead of being on the top, it's going to be on the bottom. And your 1 mole of P2O5. Now that takes you from that bottom equation back up to your top equation here. So now you want the coefficient up there for your P2O5, which is 2. And then because we wanted to end now at back how much P4 is remaining, we want to stop at the P4. So it'd be 1 mole of your P4. And since we wanted grams, we'll want the molar mass for that P4. So 123. Yeah, 123.895050. And tell me what you get for that. Everybody's just kind of filtering in, make sure you're finding the iPad where it's at signing in. Maybe it has it. It's back here. You sign in. If you don't know your P number, it's okay.
I got some regular numbers right in.
Okay. Oh, you're fine. I'm gonna go ahead and put the answer up here. Make sure you're coming up with something like 4.665 grams. That should be P4. Okay, give or take a little bit for rounding here. Okay, so what this is saying here is that the maximum production for your phosphoric acid was 14.7 grams, right? If you're making hamburgers and you have a lot of bread and only this much cheese, this is what's going to run out first. You can't make any more hamburgers after that. So when that runs out, you want to see how much of your P4 it consumed. So it consumed 4.65 grams of your original 5 grams you started with. So then you're going to take your 5 grams of original and subtract what you used up. And that's where your 0.35 grams of P4 remaining is coming from. Is that Is everyone good with that? That's a lot for one problem. I wouldn't expect you to have that much for one problem. It'd be much more realistic to have something where you said, at this point, which one is your limiting or excess reactant? Then on the next part of the problem, knowing what the limiting or excess reactant is, now tell us how much remains. So 2 separate parts. Because that's a lot on one problem. That would be like a 12 or 15 point problem. So I would expect something more like 2, 5, or 10 point problems out of this one piece. Everyone okay with that? That kind of works a little bit of the multiple reactions, your sequential reactions in there, and your stoichiometric conversions and things like that. Doing these conversions like this is reaction stoichiometry. That's taking what happened and plugging in all the values that's come from there and say, what happened with an end product? How much reactant was consumed and how much remains? Okay? What else? Other stuff you did last time that you're a little bit confused about or had problems with?
Double displacement.
Yes. Where I set in the eraser. Blow that up. Yeah. Okay. So for your double displacements,
Can't you see that?
we have a set of rules here to tell us what will displace or will not displace something else. So for single displacements, we have to have a metal activity series. For your double displacements, you have to have a solubility table. You will be given this on the test. If you didn't say that, you will have this on the test. You'll also have the activity series. No need to try and memorize that. All you need to be able to do is work through it and use it. So I'm going to scroll up a little bit here.
Can you do one with single displacement?
Let me do a double displacement first, and then we'll do a single displacement. I'm going to try and get that example in on the bottom, so keep your table there. Is everyone on this page? Does anyone not have this table?
I haven't.
Everyone have the table?
Yes.
Okay, I'm going to scroll up a
The very
little.
last one.
What number? The iron
Yeah.
acetate? Okay. I was going to scroll up a little bit so you can all see that.
Which one?
This iron acetate right here. Okay, so with this one right here, what we're wanting to see is with the double displacement, what's happening, or what we're seeing if happens, is the sodium's coming in and replacing that iron portion, and the iron is trading places with the sodium. So it's kind of like a double partner trade on this. So if something did happen, what's going to happen is the sodium is going to be the only metal over here. So what is the charge on sodium metal as a cation?
Plus one.
+1. And what is the charge for acetate?
It's -1.
-1. So for every 1 sodium, you're going to have 1 acetate. You can either write it like that, or this is the organic way of writing that, C2H3O2. It's the same amount of carbons, same amount of hydrogens, and same amount of oxygens.
What do you mean by organic way? Like organic chemistry way?
Yeah. But since we're in organic chemistry, there's no need to write it their way. We're going to write it our way. But you can write it that way if you want to. It's not wrong. So then once the sodium has taken over ownership of the acetate, the iron's going to take over this phosphate. So here, what is the charge on your iron? So your key is how many acetates you have. So you have 2 acetates there. They're each -1. So if this is no total charge over that, what's the positive charge on the iron?
Negative.
+2,
Positive?
right? Because this acetate,
Negative.
the 2 pieces have a -2, so this part must be contributing a +2. So, so your iron is a +2 here. And what's the charge on phosphate?
-3.
-3. I'm going to show you a cool trick. See those exponents? Cross them down. So this becomes 3. That becomes 2. Okay? So this was originally a +2. So what you end up with is 3 plus 2s or a +6. This was a -3. What you end up with is a -6. Okay? Now then, if this reaction does happen, these will be our products, but we don't yet have them balanced. So we need to balance it first. Okay? So 3 irons on the right, we need 3 irons on the left. When we do that, that gives us 3 irons. That also gives us 3 times 2, 6 acetates there. Okay? So we need 6 acetates over here. How do we get that?
6.
A 6 in front of that. That gives us 6 acetates, 6 sodiums,
And you need 2 in front of
and then you have 2 in front of that, which gives us 6 sodiums and 2 of your phosphates. So now that's balanced, but we want to see, do any of these form? So we have an acetate, a phosphate, and then the opposite flipped on the other side. So if you look back up here to your rules, I'm going to scroll back up now that I've got all that written there. So if you look at your rules up here, what you'll see is compounds containing an alkali metal. So these are ones that are water soluble, and these are ones that are insoluble. So these are ones that are going to form solids. These are ones that are going to be aqueous. Okay. So where on there do you see? So you're looking for this portion. What you're interested in is this portion. Do you see an acetate? What places do you see it appear at?
the second.
So it's right here. So whatever rule is talking about acetate, we want to key in on that. Do you see it anywhere down here in something that can make it a solid? Anywhere?
Yes.
Where?
The first rule.
The first rule? Well, that's our carbonate.
No, the second one.
I thought PO4 is the first.
For the phosphate, yes. So that's our other piece that we're looking for is for our phosphate. Does the phosphate appear anywhere up in the top?
No.
No. So who's the guy that appeared in the soluble portion?
The acetate.
The acetate. This guy right here is going to be aqueous. He's going to be soluble. If he appears up here in that top part, he's talking about something that is soluble. Okay? The guy that appears down here in the insoluble portion, he's the guy that's going to be a solid. He's going to precipitate out. So who's the guy that appeared down there?
Phosphate.
Phosphate. This is going to be your solid. Okay? This reaction will happen. There is a solid formed. The solid formed is your iron 2 phosphate. Okay?
I have a question.
Sure.
When will you not, like on some of them he says there won't be anything formed, or what, like are you trying to make it?
No reaction.
Yeah, no, what does that mean? Like
The
what
first one, so if you scroll down,
Mhm.
the first one's a no reaction. Will you just like go back over that? Like explain why there's no reaction?
On 9?
Yeah, there's the yeah.
H4.
So, do you want to do this one?
Yeah, I mean, you already did it in class, but maybe you can explain it differently
Okay.
so I can understand it.
All right. So if we do the same thing, trading partners down here, we do the same thing up there as we did down here. This ammonium, which is acting like a metal, will trade places with potassium, and the potassium will take the ammonium's place. Okay. So doing that, the ammonium has a what charge?
+1.
+1. It's going to pick up this sulfate, which has a what charge? -2. So if each of these ammoniums is +1, we know we need 2 of those for a total +2 in order to really pick up that sulfate, right?
Okay.
Okay, so then once you've picked up that sulfate, all that you have left now is the potassium metal and the chloride metal. If those two come back together, the potassium is a +1, the chloride is a -1, so they'll come together in 1 to 1. Okay, now you want to balance it first. So 2 ammoniums on the right, you need 2 ammoniums on the left. So that gets you 2 ammoniums, but it also gets you 2 chlorides. So you need a 2 over here. Okay, that gets you 2 chlorides, 2 potassiums, so that's good. Now what you want to do is you want to look at these 2 products you form and look back at your chart. So this time we're actually having to look at the same place, but it's two different guys, right? There isn't an acetate or a phosphate this time. There's a sulfate and a chloride. So looking for sulfate, where does he appear at? Does he appear in the top anywhere?
Yes.
Okay, where? So we have a rule for him here. Do we have any other rules for him? No. So looking like this sulfate guy, he only appears up here in the soluble portion, so our aqueous portion. What about our chloride guy? Does he appear in the top or the bottom? The top. Where at?
3.
So he's going to appear here. So both of these guys are going to be soluble to start out. Now there's only a couple things that can make them insoluble, and that's our exceptions right here. So both of these guys are immediately in the clear unless they're with one of these metals. So what you want to do then is, now that you've found them here, you're looking at their metal portion. So in that case the potassium, and in this case the ammonium. So when the sulfate rule is paired with silver, that's actually dimercury, lead, calcium, strontium, or barium, it will be insoluble. Is that sulfate with any of those guys? No. So he's still okay.
So
He's still going to be soluble. If you'd had one of those metals, automatically he's your solid. But since you don't, he's still soluble. Now the chloride guy, you're looking at his metal and you're wanting to say, are you with very similar kinds of metals? Are you with silver? Are you with dimercury? Are you with lead? Is he with any of those? No, so he's still soluble too. If both of these are going to be aqueous and no solid is formed, there's no reaction. Because all that's basically doing is taking a bunch of dissolved stuff and pouring a bunch of other dissolved stuff in there, and now all you got is a bunch of dissolved stuff in one beaker.
So that's why you're saying double displacement is 2 different compounds?
Right.
So you have to have a solid?
You have to have a solid. If you don't form that solid right there, there's nothing that really changed. Everything's still floating around in solution. But when you have that solid form, the solution's going to turn a different color, or it's going to have a white, milky solid, or some type of solid form, some precipitate. And that's a sign that we've had a reaction happen. But for these guys that have exceptions, these are the only two, your chloride and your sulfate. If they're not with one of those metals, then they're still in the clear. Is that a little bit better?
Yeah, I guess I got a little more confused too, because it's for the bottom half of it's flipped.
Yep.
I was thinking the whole thing was...
Yep. Just find where they start at though. Don't get like overwhelmed by the chart. Find where they start. If they're already soluble and they're already in the clear to start with, they've got to have something that's going to force them to not be. And if they're the opposite, if they're already screwed, they've got to have something to save them, to keep them soluble. Otherwise, they're the red herring.
Okay. And you said that he is going to give us...
You will have the double displacement solubility table. You'll also have that for single displacements, that metal activity series. Both of those will be on the test. It should be somewhere on the back page where your all your givens are. So other things, like if he has any constants for this test or anything, will be on there. It'll be on that same page. Okay, and then a single displacement. Which one of these did he not do? Let's do that one.
HCl and copper.
The HCl and the copper, that one?
I don't think you did the first and the last one.
Okay, let's do all three. How's that? We'll do the first, the last, and that one. So, 1, 4, and 5? Okay. So, with this first one, what you're starting off with is just potassium metal, solid, and you're going to drop it into a beaker that's dissolved iron chloride. And what you're hoping is that this potassium has the brunt force to come in and kick that iron out of its spot. Okay? The way you tell that is how active a metal is. So if a metal is very active, it's going to give up its electrons to someone else who's not as active, and it's going to take its place. So in this case, we want to find potassium metal and iron on our activity series here. Okay? So where is potassium? And where is iron? About middle of the chart right here. So there's your iron, and there's your potassium. If I rank higher than you on the chart, I'm more active, meaning I'm going to kick you out of your spot. Okay. Another way to think of this, if you're having trouble remembering it on the test, does gold rust very often? No. We use it a lot for jewelry and stuff like that, right? It's going to stick around a long period of time. But then think about, think about a car. Cars rust if you don't have paint on them, right? So this is more active than gold is. Okay. So as you move up the chart, you move up in activity. So potassium does have the brunt force to kick iron out of its spot, and it will. So when that does happen, the charge on this iron here, because you've got 2 chlorines that are each -1, the charge on that iron is +2. So this potassium is going to come in, kick that +2 iron out. What you have then is potassium chloride, KCl, 1:1, and just iron metal solid. Okay, this will now be your aqueous, and that's going to be your solid. So with single displacements, if you have a metal that's more active, you will start with a solid and you will end it with a solid, and it should be a different metal. Okay, now we need to balance this. So 2 chlorides here, we need 2 chlorides there. That gives us 2 potassiums and 2 chlorides, so we need a 2 in front of potassium here. This reaction will happen because you have a metal that's displacing the metal there, which is more active. Okay? So with your HCl and copper, now copper is your metal trying to come in and displace hydrogen. Is that going to happen? So look at your chart. I just barely fit it. Ooh, look at that. So here's hydrogen, and here's copper. Who's the guy that ranks higher?
Hydrogen.
Is hydrogen going to let its little brother come in and kick it?
No.
No. So this won't happen. This will not happen. No reaction. It will not happen if the metal that is a solid coming in is not more active. It cannot kick the other one out. This will not happen. Okay. What about this one? This bottom reaction. Does hydrogen have the brute force to come in and kick silver out of its spot?
Yeah.
So then you've got hydrogen and silver. So does silver rank higher or lower than hydrogen? Lower. So silver will get beat out of its spot. So when this hydrogen comes in, what's the charge on nitrate? -1. And what's the charge on a single atom of hydrogen? +1. So what you'll get is nitric acid, okay, HNO3, and just solid iron, Ag solid. Okay. It's not balanced yet. We had 2 hydrogens starting off. We still have to have 2 hydrogens ending. So that gives us 2 hydrogens but 2 nitrates. So we need a 2 in front of your silver nitrate and a 2 in front of your silver. So that reaction will happen because the hydrogen is more active than the silver there, so it will kick it out of its spot.
Since hydrogen is a diatomic molecule, would it already be H2NO3?
It will. It will be H2 here, but you have to follow rules of charge when you're talking about combinings. So just like the silver is a +1 and the nitrate is a -1, they go together in 1-to-1 proportions. You have to follow